Okay, so good morning. Welcome back to the CNC lecture sessions. On our earlier occasions, we had discussed about the basic principles of NC-CNCs, different aspects, and we had mostly emphasized on the quantitative analysis, that is the total pulse count, pulse frequency, gear ratio, and of course the resolution, accuracy, repeatability, and interpolations. And one lecture we had prepared for the applications of the CNCs in the real life situations as regard to the what is popularly known as CNC turning center and CNC machining centers. Now today's lecture will focus towards the numerical problems on the CNC, which are become very prominent for different competitive examination, particularly GATE and DSC and similar other examinations. So today we'll discuss few prominent problems from the previous year's GATE examinations. I believe that these problems, after discussion, will be able to correlate with our previous lectures and will develop the ability to solve independently in the examination. So the first problem, this is a beautiful problem which is a blending of your basic concept of metal cutting, more specifically towards the tool geometry. In this case it is a drill bit and some CNC basic syntax. Both these two aspects are combined in this particular problem. The problem statement is like that: in a drilling operation, a twist drill of 30 mm diameter with point angle of 180 degree is used. The CNC command issued to execute the drilling operation is G90 G01 Z feet 20. The datum is defined on the top surface of the work and the approach distance is 3 mm. Then to achieve a cylindrical hole depth of 40 mm, what will be the Z coordinate to be provided in the CNC command in millimeter. That means this dotted portion is basically a fill in the blanks type. Whatever result that you will obtain after calculation, that will be suitably incorporated in the fill in the blanks. To understand or to approach this particular problem, it is imperative to have a geometry for better understanding and to facilitate the calculations part. I have taken one plate of 40 mm thickness. What I was talking about, that drill geometry, particularly the drill point angle, that is very important. In this particular problem, drill point angle 118 degree is given, but in some cases it is necessary that you should remember the standard point angle of a twist drill, which is 118 degree. Anyway, it is given. Another important feature of this particular problem, as far as the answer is considered, that is this G90. G90 is the code for absolute coordinate system, and that is why the datum is defined on the top surface. So you have to identify and locate the datum. In this particular case, it is already stated that the top surface is considered as the datum or reference. So we consider, as far as the axis nomenclature is concerned, since the tool movement is vertically up and down, so this will be considered as the Z axis. So I have mentioned in this particular drawing that datum is Z0. And before the commencement of the drilling, the tool occupies a position above the top surface by 3 mm. That is told over here. So this blue color line signifies the initial starting position of the drill bit before it starts its movement for the penetration. Another important aspect associated with this particular problem, that is captured by this particular word for full penetration. Then to achieve a cylindrical hole depth of 40 mm. So if 40 mm full depth penetration is required, then considering the tool geometry, that is the frontal or the nose part. So this taper part should completely goes out of the drill, the hole of the plate, so that full penetration of the desired diameter of 30 millimeter is possible to achieve. So after passing through the hole, that drill bit should occupy a position something like this, which is shown in this particular figure. So what will be the total tool travel? This portion, so this is the starting point which I have shown at the junction of the center point. So this 3 millimeter is kept at the beginning. The depth of the hole is 40 millimeter, that is shown by the thickness of the plate, and for the full penetration, this additional amount we ought to calculate. That is the most fundamental part of this particular problem. So that is why I have mentioned, for full penetration of the hole, the tip of the drill should completely pass through the hole. Now, what will be the total drill depth? For the full penetration, if we leave aside this initial 3 millimeter, so after moving to the 3 millimeter in space, the drill tip will just touch the top surface of the job. After that, it is supposed to cover by this 40 millimeter and this additional vertical amounting to this 30 by 2 divided by tan 59. So if you focus your attention toward this tool geometry, okay, so it is something like that. So this total included angle is 118 degree. So in one side, this will be 59 degree. Now this is the diameter. So half of this will be d by 2. So we are supposed to calculate this much, right? So from the geometry of this drill tip, it is very easily can be calculated. This much portion is equal to d by 2, that is the half of the diameter by tan beta by 2, where beta I have considered as a half of the point angle. The total point angle is represented by 2 beta, which is given as 118 degree. So half of this will be 59 degree. So this much will be equal to d by 2 divided by tan beta by 2. So the entire tool movement will be 40 millimeter plus this much. So if you calculate this much part, 30 by 2 divided by tan 59, this will come as 9. So that is why the total movement will be 40 plus 9, that is 49 millimeter. Would be minus 49 millimeter. So that is the answer. Now, as regard to this particular problem, as a matter of caution, I have mentioned or incorporated 3 different points which you should remember. Since the top surface of the plate is considered as datum, the required Z value will be accompanied by minus sign. Since this top surface, that the datum is considered as Z0 and tool is moving down, that is, it is penetrating the job. So in the absolute mode, we will have Z minus 49. Now you may consider that tool is also moving in space by additional 3 millimeter, but since the Z is 0 at this the top face and we are in a G90 mode, so our answer will be minus 49 millimeter. Okay. Second thing, the approach distance of 3 millimeter would be specified in the previous block, not in the present block. That means by some way want to mean either linear interpolation or your point to point interpolation. The tool will come and occupy the starting point, which is shown over to this start point. That will be taken care of in the previous block. But as far as the drill movement is considered, that is taken care of by this particular syntax G90 01. So your answer will be Z minus 49 feed value of 20. Now additionally, I have mentioned that if G90 would have been replaced by G91, so G91 is meant for incremental mode. In that case, the tool movement would have been minus 50. That is 49 plus additional 3 millimeter. Need to consider. And what is the incremental movement from the starting point to the final destination point? So these are the small things which we should consider while solving this sort of problem. Second problem, it is not a very difficult one. Still, I have considered that this sort of problem is supposed to encounter in the ensuing gate examination. A single axis CNC table is driven by DC servo motor that is directly coupled to a lead screw of 5 mm pitch. The circular encoder attached to the lead screw generates 1000 voltage pulses per revolution of the lead screw. If the table moves at a constant speed of 6 meter per minute, then what would be the corresponding frequency in kilohertz of the voltage pulses generated by the circular encoder? For this sort of problem, once again I would like to suggest that you must remember or try to visualize the schematic diagram of the open loop system and the closed loop control system. Okay, so if you can visualize how the power flow takes place, what is the arrangement, then you will be in a comfortable position to solve this sort of problem. Now, what is the basic theme? The table speed is given that 6 meter per minute, which will be equal to 100 millimeter per second. So just convert 6 into 1000 by 60, that will yield 100 millimeter per second. Be careful, particularly in the gate examination, in which unit you have to express your answer, that is usually given within the bracket. So it has to be expressed in the kilohertz. Hertz means number of pulses per second. That is why I have converted it to the per second according to the table speed. Now, how we achieve this table speed? Once again, coming to the very fundamentals of the motion transfer, because the lead screw is coupled to the motor. So as the motor starts rotating, the lead screw also will start or will also rotate. If there is some gear in between, then there will be reduction speed. If it is directly coupled, that implies there is no reduction or change in the speed. So the motor speed and the rotation of the lead screw would be same. And the nut is coupled to the lead screw. So the rotational movement of the screw will be transmitted to the linear movement of the nut. And since the table is mounted on the nut, so eventually the table will have the same uniform linear velocity. So to accomplish 100 millimeter per second, what will be the complete rotation of the encoder? Because one complete revolution of the lead screw equivalent to each millimeter linear movement. So if we divide this linear velocity by pitch, then we will get the corresponding rotation of the lead screw per second. So we eventually get 100 by 5, that is 20 revolution per second. So revolution per second, what is the complete revolution of the encoder corresponds to the table speed of 6 meter per minute, which is given. Now the circular encoder attached to the lead screw generates 1000 voltage pulses per revolution. The purpose of installing the circular encoder is to monitor or to measure the positional displacement, and it will send the equivalent pulses as a part of signal, which will be compared to the reference values in the comparator, and accordingly the next phase of command will come, so that eventually the tool or the table reaches the target destination point. So in one, since there is 1000 pulse in one revolution, so definitely it is very easy to calculate. So if the revolution is 20 revolution per second, so the total pulse generated will be 20 multiplied by 1000 hertz. Since answer is need to be expressed in kilohertz, so I have eventually expressed in 20 kilohertz. So these are not very difficult. Only thing is that you have to carefully and perfectly visualize the schematic arrangement of the open loop and the closed loop control system. Anyway, this particular problem pertaining to the closed loop control system, because of the fact there are two key words through which it is possible to identify that this problem pertaining to the closed loop control system. One is DC servo motor, another is installation of the encoder, that is the feedback devices. Third problem, it is from GATE PI 2020. The movement along the Z-axis of a CNC drilling machine is controlled by using a servo motor, a lead screw, and an incremental encoder. That means arrangement is same. The lead screw has 2 threads per centimeter and it is directly coupled to the servo motor. Once again, the incremental encoder attached to the lead screw emits 1000 pulses per revolution. So these two problems are basically almost same. Only thing is that here pitch is defined in a different fashion. 2 threads per centimeter. That means in 1 centimeter there are 2 threads. So that means distance between the 2 consecutive threads, which is here the pitch, that will become 10 by 2, that is 5 mm. So incremental encoder attached to the lead screw emits 100 pulses per revolution. That means for 5 mm displacement, the number of pulses emitted by the encoder is 100. So what will be the displacement for 1 pulse? So that is 5 by 100. So that is nothing but the resolution of the basic length unit. That is what exactly is supposed to be calculated. Now what is the control resolution? So that becomes 5 by 100, that is 0.05 millimeter, that is 50 microns. Very simple problem. Another problem, GATE PI 2018. The work table in CNC machine is driven by a lead screw with a pitch of 2 mm. The lead screw is directly coupled to a stepper motor of step angle 1.8 degree. What is the total pulse required to move the table by 50 mm? In our earlier discussions, or I believe that it will be the lecture number 5 or 6, where we had calculated what is the total pulse count. So if you can correlate, you will find the step angle alpha is given as 1.8 degree. So the total number of steps will be 360 degree by 1.8 degrees, which yield 200. It is told that the work table is driven by lead screw with a pitch of this, and this screw is directly coupled to the stepper motor. So there is no gear in between. So gear ratio will be 1. That is RG is 1, and pitch is given 2 mm. So this, or 1 complete revolution of the motor, similarly similar will be the rotation of the lead screw, because there is no gear. So that implies 200 pulse will cause 1 complete revolution of the stepper motor, and hence the lead screw, and 1 complete revolution of the lead screw corresponds to p millimeter movement. So 2 millimeter linear displacement of the table is caused by 200 pulses. Therefore, total number of pulses required if you want to move or displace the table by 50 millimeters simply through linear interpolation, which is 5000. 200 into 50 by 2, that is 5000. That is the answer. This problem is also very simple. We cannot consider that although the term CNC is included in this problem statement, but it has got nothing to do much with the CNC. Only thing is that you have to consider that tool motion is along the straight line. That means straight line interpolation we have to adopt. The tool or the cutter is moving from the starting point 0, 0 to a final destination point 100, 100. So if the tool is supposed to move from 0, 0 to 100, 100, so following the straight line interpolation, what will be the total distance traversed? It will be under root 100 square plus 100 square. So the tool travel following the straight line interpolation will be 100 root 2, which is 141.4 millimeter. And the feed rate is employed 50 millimeter per minute. So since there is no acceleration or deceleration, so definitely the time required to move the tool along this straight line trajectory from starting point 0, 0 to final point having coordinate 100, 100, it will be 141.2 by 50. And if you want to multiply, want to express in the second, it has to be multiplied by 60. So this will be approximately 170 seconds. So there are 4 options. So eventually the option B is correct. While solving this sort of problem, there maybe initially you may have some confusion that the straight slot of 10 millimeter width and 2 millimeter depth of cut. What is the utility of these data? These are extraneous data which are not required to calculate the machining time or tool travel time. In one cut, you have to assume that, or it is implied that the width of the slot is similar to that of the diameter of the cutter, and in one cut the entire 2 millimeter depth of cut can be covered up. So these two dimensions has got no relevance with the machining time calculations. This is one of the very interesting problems that I had seen in several years question. GATE PI 2013. A circular hollow disc of 200 millimeter outer dia and 80 millimeter inner diameter is fetched at a feed of 0.1 millimeter per revolution with a depth of cut of 1 millimeter. So you have to consider a hollow thick cylinder having OD 200 millimeter and ID as 80 millimeter, and 1 millimeter facing depth of cut is applied. The facing operation is undertaken at a constant cutting speed of 90 meter per minute in a CNC lathe. The second part of the problem I will be discussing a little bit afterwards. Now, assuming approach and over table of the cutting tool to be 0, what will be the machining time? This is also a very unique type of problem. Although it is related to the CNC, but it is essentially a problem with the metal cutting. But this constant surface speed machining, this is a very attractive or distinguishing feature of the CNC machining, which is otherwise not possible in a conventional central lathe. There is a feature which can be invoked by incorporating suitable G code. Traditionally, G96 is a command by which it is possible to implement and maintain a constant surface speed during the cutting, which is as such desirable for considering different tool job combinations. But in this particular context, I would like to warn you that while preparing a particular program during implementation, during fetching operation, you should be careful, because if you maintain constant surface speed, the N will keep on increasing at a very high rate when the tool approaches towards the center. That will be inevitable to the very basic rule or basic formula, that is V equal to pi dn, that we have used afterwards. V equal to pi dn. So if V remains constant, then N will be inversely proportional to D, that is N proportional to 1 by D. So as D keeps on decreasing, N keeps on increasing. So it may so happen when D approaches towards the center, that means D approaches 0, the N will try to approach infinite. In that case, motor battery. So one should be very careful about implementing this particular code. So anyway, to solve this particular problem, let us take this particular drawing. This is the OD, this is the ID, and at any time T, the tool occupies a position which is represented by the diameter phi d, or the corresponding radius will be r. And in the next incremental time, small incremental time dt, the reduction in radius is dr. If that is so, once again, the tool movement always with a constant velocity. So dt will be equal to distance traveled by the velocity. So if you multiply feet with the RPM, you will get linear velocity, that is some millimeter per minute. So dividing distance traveled, that is the dr, by velocity, you will get the small time, that is the dt. Now see, I have incorporated one minus sign because of the fact as t increases, that means with the passage of time, the r value keeps on decreasing. Usually for any circle or circular arc, how we specify the arc? With respect to the center. From center, how much it is traced. But the machining is carried out from the outer towards the center. That is why I have taken negative sign. Then this is the equation which I was talking about. Vc equal to pi dn. So N will be equal to Vc by pi d. Therefore, dt will be equal to minus dr by f into Vc into pi d from the earlier expression. Just you go consider dt equal to minus dr by f into L. We have replaced N in terms of d and Vc. That is what exactly is done over here. dt equal to minus dr by f into Vc into pi d, and in the next step d is replaced by 2r. So after simplification, it will eventually come as minus 2 pi r dr by f into Vc. So to calculate the total time while moving the tool from the OD, that is 200 millimeter, to IT, that is 80 millimeter, you just go for the integration. So 0 to T12 T machine dt equal to minus 2 pi f into Vc. I have taken out of the integration sign because it is told categorically that velocity will remain constant and also the feed employed is also constant. So what remains? Integration r dr, limit from r0 to ri. Once again, we have to think of that tool travel is from the outer towards the inner. That is why inner limit will be r0, outer limit will be ri. So if we just change the limit, so minus minus will be cancels out. So eventually it becomes plus. So then T machine becomes 2 pi by f into Vc, half r0 square minus ri square. So the values are given. Eventually we will get machining time is 2.93 minutes. In some solutions by some agency, you find that there is some shortcut method by averaging the diameter, but that is, it has got no such scientific background. So that is the appropriate approach to solve this sort of problems. Now coming back to the second part, so the correct answer will be 2.93 minutes. In the second part, it was told the main tangency of the cutting force is 200 Newton. This portion is exclusively from the metal cutting concept, which you had studied earlier perhaps. Neglecting the contribution of the feed force towards the cutting power, that is, entire power is consumed due to cutting. What will be the specific cutting energy in joule per millimeter cube that we have to consider? So for that, we first calculate what will be the MRR, metal removal rate. That is total volume of metal removed divided by time required for machining. So volume for the cylindrical piece is pi r outer square minus r inner square into depth of cut by T machine. These are all given. T machine we had just computed as 2.93 minutes. So it should be considered as or it as a 150 millimeter cube per second. So the total energy required is force into the velocity. So cutting force is given 200 Newton and Vc is also given 90 meter per minute. So 200 into 90 into 1 by 60, because 90 is expressed in meter per minute. So eventually we have converted it to the joule per second, which yields 300 joule per second. But what is the specific cutting energy? That means energy or the power required to eliminate the 1 unit volume of material. So if you divide the total energy by the MRR, you will get the specific cutting energy, which is 300, and MRR we have just calculated 150 millimeter cube per second. So if you divide it by total energy by MRR, you will get specific cutting energy, which is 2 joule per millimeter cube. So the correct option will be 2. That is the B. This problem is a little bit unconventional. If you can recall the sources of inaccuracies, then you will find in our discussion earlier that play between nut and bolt, that is due to wear and tear for prolonged use, backlash in the gears, misalignment, all these contributes to the inaccuracy, which eventually deter the system, or for which the system suffers from final desirable position to achieve. That means what is supposed to be its destination and what the tool or the table actually achieves, there will be some error or differences. That is what exactly we call as a lost motion. So the lost motion is basically due to presence of play between the or misalignment in the nut and bolt due to prolonged use. there is a possibility that for one complete revolution of the lead screw, which is for which that knot of the table is supposed to move by the pitch millimeter, the actual real movement will be something smaller than that. That is what exactly is known as lost motion. Okay. So on that background, this particular problem is focused that XY table of AC machine is supposed to move from the point P to Q. Their coordinates are given. The pitch of the LC drive lead screw is 1 millimeter. Now, if the backlash between the lead screw and the nut is 1.8 degree, then what will be the total backlash while moving from P to Q? Now, from the P coordinate and Q coordinate, you find that Y coordinate values remain same. So, the movement is exclusively along X axis. So, what is the incremental movement along X axis? That is 51 minus 1, that is 50 millimeter. Now, given backlash is between the lead screw and the nut is 1.8 degree. That implies for one complete revolution, that is the 360 degree rotation, there will be backlash of 1.8 degree. This is popularly known as wind up error. This 1.8 degree. Okay. So for 360 rotation of the screw, the angular loss motion is 1.8 degree. Now 50 millimeter linear displacement corresponds to 50 into 360 degree rotation. So if the objective is that the tool travel will be 50 millimeter along X direction, then what will be the total number of rotation of the lead screw of the in degrees? 50 into 360 degree. So for which the total angular lost motion will be how much? So 1.8 by 360 into 50 into 360. For simplification, I have done something like that. So 360 cancels out, and if you multiply 1.8 by 50, it will come as a 90 degree. So for 50 millimeter, so for one complete evolution, that is 360 rotation, the lost motion is 1.8 degree. So when it is 90 degree total lost motion due to linear movement of 50 millimeter, the what will be the total backlash? So 90 divided by 360 into 1 millimeter, that is 0.25 millimeter. So this is one of its rare kind. So for this, you ought to remember or to consider the sources of the lost motion and what is the wind up error and total lost motion. This is the last problem. This problem, although it is related to the CNC, but it can be considered under the purview of the basic metal cutting. There is a chapter called Economics of Machining. There, on the analysis of the optimization point of view, this sort of discussion takes place. Or there, in case of CNC, there is an advanced module which I had not considered, that is called adaptive control. So adaptive control with optimization, that is how the operating variables, that is speed, feed and depth of cut, can be regulated or the optimized so that the any objective function, that may be maximizing MRR or reducing cost, anyone, or the improving the productivity, that can be maximized or minimized according to our requirement. So now this particular problem, it is told that there are two components of the cost. One is cost of metal cutting. It is a simplified version, 18 into some constant by V, and the cost of tooling is 270 into C divided by T into V, where T is the tool life and V is the cutting speed. So the total cost will be metal cutting cost plus the tooling cost. So total cost DC becomes 80 CV. So the two different components, that is the cost of machining and the tool cost itself, these two are added together to get the total cost. Now in this particular experiment, you find that C is constant. Now this T, that is the tool life from the Taylor's tool life equation, it is supposed to follow Vt to the power 0.25 equal to 150. So if we express T in terms of V and replace this T by this particular expression, then on the right hand side we have only one variable, that is the V, because C is constant. So what you have done, from the Vt to the power 0.25 equal to 150, you have to find out what is T, that would be equal to 150 by V to the power 1 by upon 0.25. So total cost becomes 18 C by V plus 270 C by T dot v to the power 4 150 to the power 4. Just we have to take the reciprocal here because 1 by t appears in this particular expression. Now total cost becomes the function of v, that is the cutting speed only. So to minimize the total cost, we have taken the derivative. There is a tc with respect to v, which is 18c plus v to the power 4. Here is v, so we have got minus, this v to the power minus 1, so it will come as minus 1 by v square plus 270 into c by 150 to the power 4 dot 3 v square. So after simplification, you will get v optimum equal to 57.9 meter per minute. Another interesting point you must consider at the beginning, that apparently it seems that the value of c is not given. Then how to calculate? Afterwards you find that when you simplify, that's the order of value of c is same, c to the power 1. So this will cancel out from both sides. So we don't require the exact numeric values of c to obtain cutting speed. Okay. So the final calculated value will be 57.9 meter per minute. So that is also a different type of problem which was set in GATE 2016. So that's all for today. So today we have discussed wide varieties of numerical problems which were appeared in previous year's GATE examination. I believe that similar type of problems will be again be set in the ensuing GATE examination 2024 and similar other competitive examination. And before that, I will suggest just to go through my previous lectures so that you can recall appropriately what are the sources of accuracies, what are the sources of inaccuracies, what are the repeatability, resolution, BLU, total pulse count, pulse frequency, and most importantly, the concept of basic interpolation, that is point to point and straight line interpolation. Okay, so that's all. Thank you very much for your patience here.